Greetings, Glenn here from West Valley College. Today we're going to talk about intermolecular forces, what's holding molecules together. Um, so we'll jump straight into the notes here. I'm going to share my screen. There we are. And so first, you have to recall something that's super basic. You might even be like the very first thing that you learn about in Chem 1A, the three states of matter that we find almost every substance in: solids, liquids, and gases. So solids, we know they got that fixed shape, fixed volume, but you can apply some heat, and sometimes you can even remove pressure, and we can get them to melt. And now all of a sudden, it has probably a very similar volume. Most chemicals, it's actually a greater volume, or therefore a lower density. But it has a fixed volume, but now it doesn't have a fixed shape. It occupies whatever shape the container is. And then you could add a little bit more heat or reduce more pressure. And now all of a sudden, kind of a dramatic change happens where the chemicals enter the gas phase, and we say that we've boiled them. We've given each and every chemical enough energy to separate from the other chemicals so that there's a lot of space in between them. And when they get close to each other, they don't have enough of a grip on each other. There's not enough of a traction there to hold them back together in the liquid or the solid phase. And that's what we're talking about a lot today with intermolecular forces. What are these sort of hooks that chemicals have on each other so that when they get close at certain temperatures, certain low temperatures, and certain higher pressures, do they get held together? And so vice versa, if you remove heat from a gas, eventually it will condense into a liquid. And if you keep removing heat, you can then freeze it into a solid. There are certain chemicals, and by the end of chapter 12, we'll learn about this a little bit more, the special conditions where this can happen. But sometimes you can bypass the liquid phase at certain temperature pressure combinations, where a chemical can undergo a transformation called sublimation, where it goes straight from solid to gas. It's actually pretty rare for most chemicals, at least at room pressure. There's only a few. But once you know about these phase diagrams, you can actually alter the pressure and then sort of force the chemical to avoid the liquid phase. And then back from a gas to a liquid is deposition. And again, we're just sort of bypassing the liquid phase. There's some of the properties of these different states of matter for one particular chemical up here in the green is just sort of a generic chemical. And actually, it looks like individual atoms there. So you might even imagine like a noble gas, a helium, a neon, something like that. It's not diatomic, so it's not nitrogen. It's not water. So here's a more specific examples of water. And we know these temperatures. So anything less than 0, ice, water is in the solid phase, we call it ice. Anything between like 1 and 99 degrees Celsius, water's in the liquid phase. Water's kind of weird in that the density actually goes up when it's in the liquid phase. And again, we'll see more about that when we get to the phase diagram at the end of chapter 12. And then a greater than 100. And these are all at 1 atmosphere. And again, this is hopefully will be more clear by the end of our chapter 12 discussions, that pressure is a key factor. And we kind of take it for granted because so much of the human population is very close to sea level, and the pressure all around the world for the last at least 150 years or so, probably more than that, has been very close to 1 atmosphere. But you probably know as you go up a mountain, the pressure goes down, and as you go drive down into Death Valley or maybe start to scuba dive, the pressure goes up, and that actually does have an effect on boiling points and melting points. And we see that the gas phase has a very low density. Molar volume, you might recall this from your discussion on gases. This is the volume that it takes to have 1 mole of the chemical. And so you can see solids and liquids are very similar, 18, 19.6. milliliters. So you can imagine that, a little graduated cylinder, it's about that much in a small graduated cylinder, about 20 milliliters. That's 1 mole. That's Avogadro's number of water molecules. But then all of a sudden, when you transform this into the gas phase, you've got 30.6 liters in 1 mole. And so this is more than 1,000 times more spread out. And it's very dramatic when you think about it in terms of thousandfold. If you take a little can of soda, all the water in there, and turn it into the gas phase, still at 1 pressure, it's now occupying the space, 1 atmosphere of pressure, it's now occupying the space of over 1,000 cans of soda. Okay, so gas molecules are really spread out. So that's sort of some of the background information before we dive into intermolecular forces. Intermolecular forces are the forces that hold condensed states together. And so those condensed states we're talking about are solids and liquids. How come we've excluded gases? Well, gases have so much energy that it's overcome these intermolecular forces. Let's say it like this. I think when a lot of people first hear about intermolecular forces, they start to think about, well, hold on a sec. You're saying there's something that's holding 2 different chemicals together. That sounds an awful lot like a bond. And there's a big difference between a bond and an intermolecular force. An intermolecular force. An intermolecular force is an attraction, and it's usually going to be considered temporary. And we're also going to see that it's much weaker than a bond. And we're also going to see, we actually see in the diagram right here, the distance between an oxygen nuclei and a hydrogen nuclei is 96 picometers, but the average distance between whole water molecules is 300. So there's this extra space here. So it's over much greater distances. And that's sort of a key thing that sort of goes along with the rest of these. It's weaker, it's over greater distances. You can imagine, though, that if you increase the attraction, all of a sudden the force wouldn't be temporary. It would become permanent. It would be stronger if the attraction was greater, and the distance would shrink. And then vice versa. If the attraction is weaker, they spread out a little bit. They become even more temporary, maybe even quicker, the attraction, before they break and fall apart and go find other molecules. And the distance will become bigger. And so the bond is sort of exactly opposite of that. It's sort of permanent, holding together, a permanent stability. It's much stronger. We're going to see that, I think, at the sort of the end of this here. And then it's over much shorter distances. So you guys are already experts on bonds. You learned a lot about ionic bonds and covalent bonds. We learned which types of bonds were more stable, which molecules, they're trying to get up to the octet rule through bonds. And then we learned a lot about bond theory in the last chapter. And now we're going outside the individual molecule. Bonds sort of describe what happens here within those 3 atoms in the water molecule. But now we're ready to sort of expand out a little bit, just one extra level. What about this water molecule and that water molecule? What's holding them together in the liquid phase? What's holding them together in ice? So that's what we're going here in chapter 12. A lot of us in the class are probably bio majors, and we may not have thought of ourselves as being super interested in electrons and nuclei, or even molecules, or even intermolecular forces. You're sort of ready for that next big thing, whole maybe organelles or whole cells. But again, the more we understand even water molecules sticking together, the better we can understand all those other things like cells. And we got a good example here of DNA coming up in intermolecular forces. So there's going to be 3 flavors of intermolecular force. Luckily, there isn't a dozen different intermolecular forces. So there's 3 types. I like to talk about them in a slightly different order than the book presents them in. I like to talk about the middle one first. It's called dipole-dipole. This is going to be whenever a molecule is polar, the force that's holding 2 polar molecules together, we call it dipole-dipole. I think it's the easiest to understand. And so from there, you can understand the weaker one, which is called dispersion. Dispersion is sort of bizarre to think about at first, but it's when a molecule is not polar at all. So it's for nonpolar molecules. And then there's sort of a supercharged intermolecular force. It's sort of an extreme dipole-dipole, and it's called a hydrogen bond, which really complicates the discussion, because I just went into a little bit on the difference between a bond versus an intermolecular force. And now I'm telling you that one of the types of an intermolecular force is called an H bond. So it's not a covalent bond. It's not a permanent bond. It's a temporary attraction. It's an intermolecular force. At some point, way off in the future, when we don't really care, that the people who already learned it, if we change all the names on them, if we were trying to make it ideal for people to learn it, we would change this to the hydrogen intermolecular force or some other name, not bond. This is only for certain molecules. The molecule must have an HO, an HN, or an HF bond, period. If it doesn't have one of those 3 types of bonds, it's not capable of hydrogen bonding. And again, it's sort of like a super dipole-dipole because H is so small and because those other 3 atoms are so electronegative. And so the strength of intermolecular forces increases as you move up here. Got the weakest at the bottom in dispersion for nonpolar. Dipole-dipole is even stronger because it's for polar. They're being held together better. And hydrogen bonds are the strongest intermolecular force. So let's dive into these examples here. So here's some examples of dipole-dipole interactions. They're showing you 2 different ways to think about it, space filling models with those delta pluses and delta minus. This molecule here, you may actually have some experience with. This is acetone. So just the chemical formula for it might be something like C3H6O. The Lewis structure for it would be a carbon double bonded to an oxygen. Sometimes the C double bond O is called a carbonyl, and it happens in quite a few different chemicals. So this chunk of the molecule right here is called a carbonyl, and it happens in a lot of different chemicals and formulas and functional groups. And that middle carbon is connected to 2 CH3 groups, which are sometimes called methyl groups on the outside. So this is acetone. This is the chemical that gets used in a lot of different nail polish removers. If it's just a small amount and it's on the other side of the room, it kind of has a sweet smell. But if it's right in your face and you're trying to remove some old nail polish, it can be very intense and almost even headache inducing. So we want to use it in a well-ventilated area. And it's super flammable. Whenever chemicals have a lot of CC and CH bonds, there's a lot of energy stored there, and it can react with oxygen as soon as there's a spark. So you want to be careful with it in sort of 2 different ways. And from our discussion in chapter 11 on polarity, we know that the CO bond is very polar. Carbon has an electronegativity of 2.5. Oxygen has electronegativity of 3.5. So the delta electronegativity there is 1. That's greater than 0.5, so it's very polar. The CC bonds are nonpolar, of course. They're the same atom. And then the CH bonds, again, by definition, are nonpolar. This is, again, the example of a bond. It's 2 different atoms. It's a C and an H. But the difference in electronegativity is so small. Carbon's 2.5, hydrogen's 2.1, it's 0.4. Remember, if the difference in electronegativity is 0.4 or less, it's just nonpolar. And so we won't draw a dipole moment on here. So if the question, and this would be a fair question from chapter 11, if the question was, is acetone polar? We'd say, yes, it's a polar molecule. it has a polar bond, and the dipoles don't cancel. And of course that's true because it only has one dipole. So if you don't have at least a second dipole, it can't cancel. Remember, there's two different ways to show a dipole moment, either with that arrow that I've got there, with the plus sign on the more electropositive one pointing towards the more negative one, or you could use delta minus and delta plus. Those mean the same thing. You usually don't see both on the same molecule, and here we're only seeing one at a time. So here's one acetone on the left, and it's got that dipole moment running right through it, pointing towards oxygen. It's polar. One side of the molecule is missing some electron density. The other side has some extra, and this lets two different acetone molecules stick together because it's kind of like magnets, but it's not magnets. So don't confuse it with magnets, but it works like magnets where the plus side and the minus side are attracted to each other. Same thing here. The minus, the delta minus, and the delta plus are attracted to each other. And sometimes we show these with a couple of dots here. This is an intermolecular force. Again, we just talked about some of the generic things of an intermolecular force. It's temporary, which means two different acetone molecules might fall away from each other and form new intermolecular forces with new acetone molecules that come in. So they're temporary. They're really far apart from each other, the molecules compared to the covalent bonds. And they're very weak. The reason you can smell acetone in the room, even if it's at room temperature, is because a lot of it's getting evaporated. If you have a little cup at the, depending on the temperature, a couple hours later, it might completely evaporated. You've now filled the room with those acetone molecules. And a little while later, it will have just sort of dissipated and maybe even been completely swapped out for the air in your house. And they're just showing it in a slightly different way with the electrostatic map, but the same thing is happening. You got a dipole moment and a dipole moment, and the plus side of one dipole moment is attracted to the negative side of another one on a neighboring molecule. And so this was one thing that sometimes people get a little bit confused on is how come they're only showing two. This would keep going on for a lot of repetitions in the liquid phase. So you would have another acetone here. Now, liquids are constantly moving. There's actually sort of an interesting quote, which I hadn't really heard of before at the very beginning of chapter 12, talking about trying to imagine what's happening with these liquid substances. It's by someone named Roald Hoffman, and he's calling it's a wild dance floor there at the molecular level. When we look at liquid in a container, it looks very still. It doesn't look like it's moving at all. But if you were somehow able to shrink down and see these individual molecules, they're bouncing around, they're twirling, they're forming intermolecular forces and then falling away and making new intermolecular forces. So there might be, three in a row 1 second, but then one falls away and then comes back in a different place or weasels in between them. But what we're saying is most of the time, most of the molecules are forming some intermolecular forces, some of these attractions between delta plus and delta minus. If you were to take a picture and look and count the number of molecules, you'd see most of them are oriented this way. Can you see that? Yeah, most of them are oriented delta plus to delta minus, but that doesn't necessarily mean all of them are. Probably the more polar they are, the more, the bigger this dipole moment here, the more they're going to stick together. So here's some examples of what I was just talking about there. We've got dipole moment on the x-axis. So propane is nonpolar. It doesn't have any polar bonds. Dimethyl ether is a little bit polar, and we see the dipole moment is much bigger. And then you get bigger and bigger and bigger for these 5 molecules. Acetonitrile has the biggest dipole moment. It has the largest delta plus and the largest delta minus over here. And they're comparing the boiling point in Kelvin. And we see that we go from about 225 to about 350. So 350, that's like 80 Celsius. And 225, that's like negative 50 Celsius. So propane boils way before room temperature. You just pour it out at room temperature and pressure, and it's boiling. But if you put your hand on it, it's cold. And that's because the intermolecular forces aren't strong enough to hold it together at room temperature and pressure. But acetonitrile has such an enormous dipole moment. So many of the molecules are held together so tightly that you pour it out, it's a liquid. It's actually kind of a greasy liquid. It's a weird chemical to interact with. It's just a clear liquid, but you can tell that it's not water when you're pouring it around and stuff. You have to heat it up to over 80 Celsius, or around 80 Celsius, to get it to boil, at which point, of course, it would feel hot. So what can we say there is the greater the dipole moment, the greater the attraction, the greater the boiling point. So the greater the dipole moment, meaning the more polar the molecule, the stronger the IMF and the higher the boiling point, the melting point. So that's sort of the key takeaway there from dipole-dipole. So now, and another thing that we could say is that any polar molecule has dipole-dipole attractions. Now let's talk about the weaker one. These are called dispersion forces. Dispersion forces, as I mentioned, are a little bit tricky to wrap our heads around. So here we've started really simple. This is a helium atom. If you look in that nucleus there, there's 2 protons, 2 neutrons, and 2 electrons. And so those 2 electrons are in a 1s shell, which is spherical. They're attracted to the nucleus, but they're spending 90% of their time within this shell. And so they're kind of moving around, and they're moving around really fast at some fraction of the speed of light, some pretty significant fraction of the speed of light. And so in this first scenario, you got a region of electron density on one side of the atom and on the other. And then what they're showing here is sort of taking a photo of the atom every sort of split second. So they wait a little bit of time, and you got the electron here and the electron here. They're still sort of on the opposite sides of each other. And then you wait a little bit more time, and all of a sudden, through just their previous movements, I guess, now the 2 electrons are pretty close to each other, and they're more on one side than the other. And that's giving rise to a delta minus and a delta plus. And up to now, it might look an awful lot like dipole-dipole. The thing about this is that it's an impermanent dipole. It's very temporary. It's not based on covalent bonds and electronegativity and sharing those electrons in a covalent bond. It's based on electron movement. And through this random movement, when electrons sort of align on one side, causing a temporary dipole. So that's what we should think of and say here for dispersion forces. And the weird thing about dispersion forces is they can start to induce these dipoles in neighboring atoms and molecules. So here's sort of a more formal version of it. It's an instantaneous dipole on any one, you could just say atom, because we're going to see a lot of molecules have intermolecular dispersion forces. On any one atom induces instantaneous dipoles on neighboring atoms, which then attract one another. So here what they're showing is that, let's again focus on the middle one here. Again, after some amount of time, maybe the 2 electrons in the helium atom align on one side and create that instantaneous and temporary partial negative on one side and the partial positive on the other. That partial negative on one side then kind of chases the negative atoms to the other side in a neighboring atom. So that's where the induces come from. One atom's electrons affect the electrons in neighboring atoms. So that partial positive on this side of the helium is attracting some electrons, a partial negative on a neighbor. So we see that again, these kind of spread out throughout the solution. Again, they're instantaneous or temporary. They're pretty far apart. And another key thing to know about dispersion forces is that they are the weakest intermolecular force. Another thing that we should know is that every molecule, if even helium has intermolecular forces, every atom or molecule with electrons has dispersion forces, which therefore means every chemical. Okay, so like we did before with dipole, we talked about when does that intermolecular force increase. We see that dispersion forces increase in two different ways. So I don't know if the textbook talks that much about this, but sometimes dispersion are called LDF, London dispersion forces. They're kind of interchangeable. London was one of the scientists that sort of first proposed these. Dispersion forces can increase in two ways. The first is shape. So both of these chemicals have the exact same number of atoms. They have the same molecular weight. That means they have the same number of electrons. But N-pentane is more sort of linear. It's more flat. It's got larger surface area. So that's what they're calling here, a larger area for interaction. Whereas neopentane, because the four outside carbons are bonded to the middle carbon, it's a little bit more compact. They're showing it almost as a sphere. Each of those five carbons is tetrahedral, but it's just a different shape that doesn't allow for as much interaction. And so longer molecules have higher dispersion forces, and more compact molecules have smaller dispersion forces. And so even though they have the same chemical formulas and they have the same number of electrons, N-pentane would boil at a slightly higher temperature than neopentane. So the boiling point over here is greater than the boiling point over here because of shape. And the other thing is due to size. So again, we sort of eliminated the variable size on the left. Those were the two molecules, the exact same molecular weight. But now, when we think about size, helium only has 2 electrons, neon has 10, argon has 18, krypton has 36, xenon has 54. And we're seeing the molar mass goes up, which means also the number of electrons goes up. Also, size increases this way. We know that those last electrons, so electron shell, we'll call it the valence electron shell. We know that in helium, and that's just a 1s, and neon, it's 2p, argon 3p, krypton 4p, xenon 5p. And we know that each time you go up a number in electron orbitals, the size of it increases. So that's what they're showing here. they don't have the number on it, but the radius or the diameter or the size of the atom is increasing. And that's going to make the dispersion forces a lot stronger. And so that's sort of the final point here, is that dispersion forces, they are just correlating it to molar mass. I don't think that there's like a good explanation for why molar mass would affect dispersion forces. It's more about these other things: number of electrons and the size of those valence electron orbitals mean that they're going to be more able to either induce or be induced. And so then these temporary and instantaneous dipoles are going to be a little bit stronger. So even though we started with helium, helium has the weakest dispersion forces because it's the smallest. And we see that over here with the boiling point in Kelvin, 4 Kelvin. So you have to take helium all the way down to 4 Kelvin to get it into the liquid phase. And we see as we get bigger, the boiling point also increases. As you get more electrons, as you get a bigger electron shell, the dispersion forces increase. And so here we can kind of see that again with the number of carbon atoms in a covalent molecule. So they pick some that are usually, around, I think they're liquids at room temperature. So pentane has 5 carbons in a row, hexane 6, heptane 7, octane 8, nonane 9. Notice how they didn't pick molecules with different shapes. So a lot of these molecules could have been like more bunched up. There's a lot of chemicals with 9 carbons, but they'd be more spherical and less stretched out. So they picked all of the really stretched out. That's what that N means. It means sort of linear or in a row. And every time you add a carbon, every time the molar mass goes up a little bit, every time you add a carbon, you also have to add 2 more hydrogens. So that's 3 extra atoms plus all their electrons. And so there's more opportunities for dispersion forces when they sort of get pushed against each other. There's more surface area. And again, we see the boiling point increase. And this would keep going the other way too. If you had C4H10, this is butane. This is that liquid that you can see in some of those lighters. Sometimes the like a little handheld lighter, you can see the liquid at the bottom, but it's evaporating pretty quickly. And you open it and it's evaporating that quickly. It evaporates at negative 0.6 Celsius. Its molar mass would be about 58. So it would be around here and around there. So you can see the trend continues. It's just, it would be a gas at room temperature. That's right. 20 is room temperature. So, and then that keeps going. Propane and ethane and methane all get lower and lower and less, and lower, but they're all gases at room temperature and pressure. And then the same thing will go the other way too, where C10H22, you could expect it to have even a higher boiling point. At some point, you get so high, like if you got up to C40H82, this would be a solid at room temperature and pressure, and it would be in a very waxy consistency. And in fact, candle waxes, the molecules in like candle wax or different waxes, have really high carbon counts. So that's solid linear molecules, and intermolecular forces, it's only dispersion. They're still all nonpolar. So these are all nonpolar. They're all linear. They all have the same general shape, but again, bigger, more atoms, more electrons, more opportunities for dispersion forces, the tighter they get held together. So even though dispersion forces are the weakest of all of our intermolecular forces, if you have enough atoms, if you have enough opportunities for dispersion forces, they can get glued together and get locked into that solid phase. So far, we've learned about dipole-dipole polar molecules and dispersion forces for nonpolar molecules. And something really interesting happens when you try to mix something that's polar, that has dipole-dipole, and something that's nonpolar, that's only being held together with dispersion. They don't really mix. And it has given rise to this phrase, which I'm not really a big fan of. It's called like dissolves like. And the reason I don't like the phrase is because it doesn't teach you what it's trying to learn. You have to know what it means to understand the phrase. And so it's sort of a useless thing. I guess it's 3 words that sort of simplify the idea. And if you remember it, you'll be, better off on questions and stuff like that and thinking about the chemicals you're working with. But what it means is that polar dissolves in polar, non-polar, and again, that's chemicals with dipole-dipole intermolecular forces. Non-polar dissolves in non-polar. And so these are the chemicals with dispersion forces. And what it really means is that they don't mix or dissolve in each other. Polar will not dissolve in nonpolar. So if you take a chemical that is very polar and has a lot of dipole moments and a strong dipole moment, you have another chemical that doesn't have any polar bonds and is non-polar, and the only thing that's holding it together are dispersion forces. And you pour them together, this really interesting thing will happen where they separate from each other. And what's really happening here is the polar molecules are pushing the non-polar molecules out. And it doesn't really matter if it's up or down. The thing that is more dense is on the bottom. So more dense on the bottom. And there are some non-polar chemicals that are more dense than water, and you'll learn a lot about those over in OChem, but they sink to the bottom of water. But we've got this layer here. The polar molecules have pushed the non-polar molecules out. And the reason that I'm saying that is because it's much more stable for polar molecules to be stuck together with those dipole moments. And if they're dissolved in each other, what that kind of means, especially if you have similar volumes, is you'd almost need alternating molecules. You need a water and then a pentane, a water, a pentane, water, pentane. And if you had that arrangement of chemicals, you wouldn't be satisfying any of those dipole moments. You wouldn't have any of those dipole-dipole attractions being held together. And so when they do find each other, they push a pentane out. And then it happens again and again and again. And eventually you get 2 layers. And we've all seen this happen with Italian dressing. When you pick it up off the shelf, you got those 2 layers, oil on the top, water on the bottom. You don't want to just pour it out like that because you only get the oil. So you shake it up really, really good. And then you get sort of this weird mixture before it re-separates out. So here's our 3rd intermolecular force, hydrogen bonding. Hydrogen bonding is the strongest. And it says it right here, when an H is bonded directly to FO or N, and again, that means you need an HO, you need an HF, or you need an HN bond. If you don't have one of those 3 bonds, the chemical doesn't have hydrogen bonding. And again, it's called bonding, but it's not a covalent bond. It is a intermolecular force, or an intermolecular force. The example that they've pulled here is HF, and HF is a good example to pull because it is sort of the simplest chemical that's capable of hydrogen bonding. I want to dive a little deeper on HF and what's going on here. So if you think about HF and you draw the Lewis structure, we know hydrogen brings 1, fluorine brings 7, you got 8 valence electrons. You put 2 in the bond, there's 6 more. Fluorine, we know, needs 6 more to satisfy its octet. So there's the 8. Hydrogen's fine with just 2 because it's in the first row. So now you got this HF molecule. Let's dive a little deeper on it. Hydrogen has 1 proton. Fluorine has 9 protons. I'm not going to draw those lone pairs around fluorine. Fluorine is just holding those as it is. Hydrogen doesn't even have a core electron, right? Those 2 electrons are sort of in its 1s. So if you think about where the electrons are and then the electronegativity here, fluorine is 4 and hydrogen is 2.1. This is a very, very polar bond, and the dipoles don't cancel because there is only one. So it's a very polar molecule. And if you think about where these electrons are, I'm drawing in sort of the electron cloud. What's going on here? So if you see those two electrons, they're spending a lot more time around the fluorine than they are the hydrogen. And this creates a very interesting opportunity for another HF because, I'll leave it there for a second, we've got that dipole moment. We've got a delta minus, all that extra electron density around fluorine. I haven't even factored in those lone pairs, but that's probably going to even add to it. And then you got the delta plus over here. And so when you take this molecule here, these extra electrons that are on the delta minus on this fluorine, they can get very close to the nucleus of the hydrogen in a neighboring HF, right? There's no core electrons. The two electrons in the bond have been pulled way to the other side of fluorine. And so that's what a hydrogen bond is. It's when a very electronegative atom on one molecule can get super close to the hydrogen nucleus, and you got this really strong intermolecular force, which again isn't that strong compared to covalent bonds, but it's stronger than both dipole and dispersion forces. Sometimes I've heard hydrogen bonds be called a super dipole. It's an intermolecular force for the same reason a dipole, but again, it's super because of the reason I just sort of explained there, where the hydrogen has all of its electron density on one side, and that negative atom can kind of see the nucleus and get really close to that positive charge. And then you've got these alternating pluses and minuses holding a bunch of HFs together and holding it in the liquid phase even tighter than you would expect based on its size. And so here's two different molecules. They have the exact same molar mass. One of them, I don't know why they didn't show the Lewis structure here. Ethanol has an OH, so it's CH3, CH2, OH. Dimethyl ether does not have an OH. The oxygen is connected to two different carbons. So there is no OH here. So even though they have, I guess they kind of showed it over here. They have the same molar mass, but look, the boiling points are very different. Almost 100 degrees different. Dimethyl ether boils at -22. So again, you have to pull it out of like a -80 freezer or something like that. And when you pour it out, it starts boiling immediately. As soon as it gets up to -22, it starts to boil. But ethanol, same molar weight, same size. The only difference is that there's an H on an O, and that means two different neighboring ethanol molecules can get really close to each other and participate in this hydrogen bonding. It's just a liquid, and it's boiling at 78, which is 20 degrees lower than water. But it's a liquid. It's going to hang around for a while. Here's what the hydrogen bonding looks like in water. Because water has those, the oxygen has those two lone pairs, it has two regions that it can interact with an H. And then the H's are sort of delta plus, so they can interact with the oxygen on a neighboring one here. So on average, in water at room temperature, each water molecule is through hydrogen bonds is attracted to 3.5. So that means one water molecule is surrounded by 4, and the other one's surrounded by 3, and the average of 3 and 4 is 3.5. But again, they're temporary. So one might something might come in and bump one water molecule and it rotates around and it breaks some of its hydrogen bonds, but then it reforms them somewhere else. So the three that were remaining rearrange. And so you have this orientation where you have an oxygen, then a hydrogen, then an oxygen, then a hydrogen, then an oxygen. This alternating pattern because the delta pluses and delta minuses are sort of lined up. So let's try a couple quick questions on some intermolecular forces here. Which substance would you expect to have the highest boiling point? So highest boiling point means strongest intermolecular force. We've got methanol. We've got carbon monoxide, which has an interesting Lewis structure. And we've got nitrogen, your classic triple bonded molecule. Which substance would you expect to have the highest boiling point? Well, actually, you would expect them to sort of go in this order. This would be the lowest. This would be the middle. This would be the highest. How come I said that? Well, first, you might want to look at whether it's polar or not. So N2, those are the same atoms. So that's definitely non-polar. What's its intermolecular force? It's just dispersion. What about carbon monoxide? Well, the CO bond is polar, 3.5, 2.5. The oxygen is more electronegative. So two different neighboring carbon monoxide molecules could interact with each other. So you'd say, yes, it's polar, which means it's capable of dipole-dipole attractions. So therefore, it should have a higher boiling point than nitrogen. And the reason we're comparing these three molecules is that they're very similar in size. If you have one non-polar molecule, but is much bigger than a small polar molecule, it can be kind of tricky. So usually we're comparing either the same size, different intermolecular forces, or the same intermolecular forces, but different sizes or shapes. So this is 32, 28, and 28. So very similar molecular weights. That's why we're comparing them. And what about methanol here? Well, it's got a very polar bond here. OH bond is very polar, and the CO bond is very polar. And oh yeah, H hydrogen bonds are when a molecule has an OH, an NH, or an FH. So yeah, this is polar. The dipoles don't cancel. And it has hydrogen bonds. Oh, one thing I meant to say on the last one, but I forgot. But carbon monoxide has dipole-dipole and dispersion. Quite often we don't talk about the dispersion because the dipole-dipole will be a lot stronger. But same thing up here with the methanol. It's got hydrogen bonds. It also has some dipole-dipole attraction through that CO bond. Maybe two different neighboring COs can get near each other and form a dipole-dipole. And it also has dispersion. So the strongest intermolecular forces also have the ones that are weaker. But again, we usually just talk about the strongest one that's present. With N2, the strongest that's present is only dispersion. With carbon monoxide, the strongest is dipole-dipole. So a lot of times people won't even mention dispersion. Same thing for methanol. The strongest is hydrogen bonds. It's the only one with hydrogen bonds, and so you would expect it to have the highest boiling point. And I don't have them listed right here in front of me, but I can guarantee you that it is. It's the only one that's a liquid at room temperature and pressure. Nitrogen boils a long time ago, and even carbon monoxide would too. One of these compounds is a liquid at room temperature and pressure. The other two are gases. Which would you expect to be a liquid and why? Again, we're talking about very similar sizes here. So we're mainly looking at the different intermolecular forces. We've got formaldehyde, looks like dipole-dipole to me. No OH, NH, or FH, and the CO is polar. We've got CH3F. You might remember from our discussion on polar molecules that if one of the terminal groups is a lone pair or a different atom and it's got a polar bond, then it's polar. So this is also dipole-dipole. So far, I don't have any hints. You might expect that CF is a little bit bigger of a dipole, so it might be a little bit higher of a boiling point.
But so far they seem very similar. But H2O2, hydrogen peroxide, do you see what the strongest intermolecular force is? Oh, it's got OH. It's just like water. So it's hydrogen bond as well as, I don't know if you can really say this one's got dipole-dipole because I don't see any other polar bonds besides OHs, but hydrogen bond, but it also has dispersion. So hydrogen bonds, that's stronger than dipole-dipole. So this is much more likely to be a liquid at room temperature and pressure. And therefore, these are probably our two gases based on what it said up in the question. So now I hope that you're feeling a lot more comfortable with intermolecular forces and looking at a chemical formula. Don't give up there though. Don't try to figure out intermolecular forces from a chemical formula. You have to draw a Lewis structure. Then you have to think about if it's polar or not, which again means going through that decision tree. Does it have polar bonds? Do the dipole moments cancel? If it's non-polar, it's just dispersion, like N2. If it's polar and doesn't have an OH, NH, or FH, it's dipole-dipole. If it's got an OH, an NH, or an FH bond in it, when they say OH, NH, and FH, this is kind of misleading because the only molecule that can have an FH is HF, right? You can't have other bonds on F, it's always terminal. You can't have other bonds on H, it's always terminal. So if you have a hydrofluoric acid, just HF, or the molecule has OH or NH. And these are make a lot more sense because you could have any number of other bonds to the other side of the oxygen or the nitrogen. Then you have hydrogen bonds. It's going to be the strongest as long as the size is about the same.